the host would show the person 3 doors. I don't think they had doorknobs, but oh. And behind 2 of them would have been a goat. Right now, if the guy wants a goat, then he would be happy. But normally, behind the 3rd door would be a boat, or it doesn't have to rhyme with goat, but it could be a car, a trip to somewhere. You with me? So 2 losing doors and then 1 winning door. So the interesting thing, question to ask is, this is the way it would work. I'll pick a door, 1, 2, or 3. 3. Okay, that's what I heard. And then, as the host, I would open up door number 1 and show you that behind door number 1 there's a goat. And then I would ask you, do you want to switch doors? You guys with the process here?
Let's make a deal.
Dude. So, the question is there an advantage doing one, switching or staying? Is there an advantage? And your brain says, no, what the hell? But reality says, yes, there's an advantage to do one or the other. You guys with the process, the premise. So let's investigate why. Let me actually do this. I'm going to immediately go to making this 1,000 doors. Okay, thank God I'm not going to draw 1,000 doors. And you pick this one. You with me? What's the probability? Let me see how much you know about probability. 1,000 doors, right? What's the probability you pick the winning door?
1 out of 1,000.
So the probability of you pick the winning door is 1 out of 1,000. Is that a good probability? No. So if you had to put money, if somebody else had to put money on you're picking the right door, I would put a lot of money on that because overall I'm going to expect to make some money. It's only a 1 out of 1,000 chance I'm not going to make money. I can deal with that. That's better than normal. And then the host opens every other door. Go, go, go. Poor little deformed goats. Little deformed goats, little deformed. Except for this door. He doesn't open that door. He says, now, do you want to switch? So, 2 things. Either we picked the prize. Is that a good chance that happened? No. So either we picked the prize and we stay, or we didn't pick the prize. And why didn't he open this door? Because the freaking prize is there. You guys understand it? Does that make sense? So it's better to switch. And the fewer doors, the harder it is for a brain to realize that. But why did the dude open every other door except that one? What's the most likely thing? Because that one has the prize. If he opens the door with the prize, the whole thing is shot. Right? It's like, why the hell is that guy the host? That's stupid. That's not what you do. So if I come back to here, what's the probability we picked the winning door?
1 out of 3.
Good. It's still less than half, right?
Yeah.
So there's a 1/3 chance we picked the prize. So 1/3 of the time, doesn't matter which door he opens. From the host's perspective, if you pick the winning door, he can open either one of these. That happens 1/3 of the time. The other 2/3 of the time, one of the doors is going to have the prize. He's not going to open that door, is he? Is he going to open that door? Because then then he's like, do you want to switch? Maybe the other goat looks better. He was not going to open the door with the prize. I really hope you guys are with me a little bit. This is a neat problem because it illustrates how the human brain, it's not biologically instinctive probabilities aren't. That's why it's difficult sometimes. They go. So your probability of winning doubles if you switch doors, because 2/3 of the time the door he didn't open is going to have the prize. Now the thing people hear is, I'm going to win if I switch. Well, that's bullshit. So if you lose, you're like, well, that's crap. You are twice as likely to win. Doesn't mean you're going to win. It means your chances are better. You with me? I like it. So a lot of people hear stuff like, it's going to increase the chances of this. So like, I'm going to do it, so that's going to happen. No, it's going to increase your chances of this. It doesn't mean this is going to happen, whatever that thing is. All right, maybe. Okay. So if you didn't understand that, oh well, it's all right. I'll deal with that. But it's a really neat thought process in there. Okay, just take a step back. We did the whole thing with the birthdays thing, right? Right, where we saw, and there were several people that had the same birthday, weren't there? Or no? Did anybody have the same birthday? Oh, we didn't do that? Oh, shit. Oh, I did that with my 120 class. Okay, do this. All right, here we go. You ready? So right now, would you say the odds are decent, or how do you feel about the probability that two people in here have the same birthday? How do you feel about that chance?
Yes.
It's possible, right? But do you think it's likely? Do you think it's more likely to be true than false? All right, good. That's the right instinctual answer, which means it's wrong. So do this for me. Write the day of your birth. So take a blank sheet of paper. I'm gonna play along with you. I probably shouldn't write on the back of somebody's. Oh, that's mine. This is mine, huh? I'm gonna write. So just this. So if you were born on July 12th, just put the number 12. I'm gonna call you by month. I'm just gonna put 21 because I was born September 21st. Anybody else? That would be neat. No. Okay. So just put the day. If you're born on October 3rd, put the number 3. All right, so everybody with me? If you don't have a piece of paper, ask people. Don't write in your arm. I etched it in my arm. It's like, holy shit. All right, so where are my January babies? Hold up your sheets. Are you guys ready? January? Nobody was born in January. Nobody in January? That is neat in itself. Our odds just went up a little bit. Nobody's born in January. What's 9 months before January? I don't know. I always think about that. I was born in September. 9 months before September, it was cold, wasn't it? So, all right. February. Where are my February babies? Oh my God, I can't read. Write this big so I can read it. I need to be able to read it. Sorry. Let's try this again. You did good. Write the number big. 18. Well, I'm done. I'm done. Is that today? Holy shit! I don't have a clue. 7th, 21st. So you guys, that's awesome. Happy birthday. Did you bring cake? It's the reverse birthday rules. What the hell? Real quick, just for shits and giggles. Sometimes I get to November. One time I was taken out to December and I started sweating bullets. One semester, I think nobody had the same, and that of course, all you need is about 30 people in a room to have better than 50% odds, and we got plenty more than 30, right? And the problem, the mistake our human brain makes is we think nobody has my birthday. Nobody has my birthday, right? Now, see, you guys are wrong. Nobody has my birthday, but the thing is, any two people, so the chances go way up. If I said, what do you think that somebody else has the same birthday as you? You're like, no, I put money on that not being true. But it's not just you, it's any pair of people. And how many pairs of people are in here? A lot. So the chances go way up higher than our brain immediately thinks. Oh, we got one more player. What month were you born in?
What year was it?
Month.
May.
May, okay. Sit down, get a sheet of paper out, and put the day you were born on it. Do it. All right. What year is it? No, sorry. February, where are we at? March. Where's my March babies? Just to finish this out, 5th, 27th, 18th, 5th. Look at that. 5th. Holy shit, there's a triplets. In a weird way. That's awesome. 4th, cool. March, April. April is you. April 11th, right there. Okay, I like it. No January's, 1 April. I think. March, April, May. 22nd, 30th, 20th, 25th, and 4th. Okay. May, January, March, June. 18th, 10th, 11th. 18 in general is a key day for some reason. All right, 10th, 11th. Okay. July. 18. Is this 21, 24, 12th? And 2nd, okay. August 26th and 23rd. September 25th, 22nd, 8th, 12th, 16th, 3rd, 8th. Wasn't there an 8th? There's an 8 right there. Sweet. Holy shit, how many is that? That's a lot. October 19, 29, 8, 4. November 1st, 4th, 18th. The 18 is crazy. 28, 25. That's going to be like my Jim Carrey 23 thing. 18. What was that? November? December. 6th, 1st. All right, that's everybody. All right. February 29th. No. Leap year. All right, that's kind of neat, though, isn't it? I mean, that's probability. It's neat that it's counterintuitive very often, but it's also frustrating, right? Especially as students, you're like, well, that's why. But I want you to realize it's not something hardwired for us to understand, but we only understand enough to keep us alive, right? Which way is more likely that a tiger is going to attack me? That way, so I'm going to go that way. Okay, that's the basic amount of probability that we have innate to us. It's just what's going to keep you alive, buddy, right? And then once you get past that, it's like, holy shit, it's some really counterintuitive stuff. All right, so let's bring it back down to some terminology. And by the way, just a procedural note. Bless you. I don't know if you guys realized on your homework sheet it says double quiz on chapter 3. So probability is sort of its own thing, and we take out of it some stuff we're going to use later. But so I give probability chapter its own little double quiz, meaning it's a quiz that's twice as long and counts twice as much, right? And then it won't be on a test again until the final. So like the next test won't have any probability stuff from chapter 3 on it. It's its own little thing. Sometimes I try to teach it first and that didn't work. Let me see, where am I? Oh, okay. So when you're investigating the probability of something occurring, you actually, so for example, if I ask you what's the probability if I toss a coin, flip a coin, Jeff? Flip a coin, what's the probability that it won't flip? No, that it'll be heads. Alright, did you actually flip a coin to figure that out?
No.
No, you didn't. Does anybody have a coin?
Maybe.
Everybody with a coin that wants to play along, throw it at me. No, I'm joking. Anybody have a $50 bill? No. Anybody with a coin? Do I have a coin? I have a coin. I can play. Everybody want to play? All right, you ready? Oh, look at that. You got one that you put on a train track? It'll still flip, right? And you can see what it's at. All right, I got a quarter. Ooh, I'm big time. All right, so flip it and just think and just look at what it is. All right. So, how many guys who just played along with me? How many guys got heads? All right, 1, 2, 3, 4, 5, 6, 7. So there are 7 heads. How many guys got tails? 2. I like it. Thank God. So what's the probability? So this is the theoretical probability. Kind of makes sense. It's based on the theory. It's based on the fact that why is it 1 out of 2? Why is it that?
2 possibilities.
Because there's 2 sides, and one of them matches what I'm looking for. That's the general idea behind any probability. What goes on the bottom, the total number of things it could be. What goes on the top, the total number of things that matches what you're looking for. Do you notice how I talked slower than normal when I said all that? That's probably a note. So the top in general, probability of some event A is the number, on the bottom is going to be the total number of things that could happen and on the top is the number of things matching what I'm looking for. So in this case, matching A. So the probability of heads, there's 1 head out of 2 total sides. That's why it's 1/2. Right? And you're like, man, I've never thought of it that technically before. But yeah, okay. You guys cool so far? Now this is not going to be theoretical. According to our observations, so based on our observations, what would the probability of heads be? 7 out of 9. I like it. And does that freak anybody out that we got 7 heads out of 9 flips? Does that freak anybody out? No, right? If I flipped a coin 500 times, so I'm sorry, real quick. This is called empirical probability. Actually, let me double check. I can't remember if this book calls it the same thing I do. Oh, it's not here yet. Oh, there it is. Yay. Empirical, yes. Sorry. So empirical very often is used to reference science classes because empirical is based off observations, right? So empirical probability is probabilities based off of observations. Theoretical probability is probability based off of just all the possibilities. You don't actually do something. How are we doing so far? So what I was just about to say deals with the connection between these two. Those two have to be connected somehow. That was neat. So the fact that this did not come out to be 1/2 does not freak us out. But if I flipped a coin 500 times, two things. One, I'm worried about my life. Nobody's calling. Oh, sorry. Flip the coin 500 times. I would expect to get how many heads? 250-ish, yeah. And where's 250 come from? So what does this really mean? I love my little brother very quickly. He always says, Jeff, do you still teach probability? I'm like, well, yeah, Jim. And he says, well, why are you doing that shit to these poor kids? It's 50-50. Everything's going to happen or it ain't. I'm like, Jim, I'm so happy you're not a doctor. Right? Going in for some routine thing. What's my chances, doc? Oh, it's 50-50. What? No! Or a meteorologist. It could snow or not. But I understand what he's saying. But at the same time, we do use probabilities to estimate and then to figure out what's the best possible thing I could try to do. Right? That's how we use probability. The probabilities ever tell you exactly what you should do? Of course not, because they are honest. Real life, you can't get a definite thing. This is definitely what you should do. Never, ever will you get that. Sorry, if you hope that. So the connection between these two is, if I do this often enough, the ratio should approach this. If it doesn't approach this, what's probably true about that coin?
It's off.
Probably weighted to one side. You with me? And that, of course, is going to be the next thing. What we do with probabilities is we test claims. You know, like do drug testing. You can do coin testing. If you flip it up 500 times and you get 450 heads, that is very, very strong evidence that it's weighted. Is it definitive proof? No, because could I flip a coin 500 times and could I get 500 heads, even though it's a fair coin? Of course, but if I did, that would freak me out. If you flip a coin 500 times, and so you expect 250, and you got 400, would you be freaked out? A little bit. If I got, so another thing we'll talk about later this semester is, okay, where's that line between freaked out and not freaked out? Where's that line? I don't know. We're going to talk about that later. All right, how are you feeling so far? So we got theoretical probability, empirical probability. The connection between them, you're going to love this. It's called the law of large numbers. Do something often enough, and this should become this. How are we doing? Does that make sense? Theoretical is what I expect to happen in the long run. On any individual coin toss, does this mean shit? No. That's where people freak out. Any individual trial that I run, probabilities don't mean a damn thing about it. Anything could happen there. But if I do something 20 times, and there's a 50-50 chance of something, then I should expect 10 of those things to happen. Will 10 of those things definitely happen? I don't know. Somewhere around 10, right? How are we doing so far? Are we? Okay. So, but again, that's a good point. I keep previewing what's coming, but let's say, I always pick on Shaquille O'Neal, but even though he's not been playing ball forever, but he was on the wrong team, was on the Lakers. Oh, God, Lakers. Kobe's leaving. I like Kobe's abilities, but he was on the wrong team. Let's say Shaquille O'Neal made 30% free throws. right? I'll be nice. And let's say he takes 20 free throws. So I want you to see the connection between percentage and probability. What would you say the probability is that he's going to make a free throw? 30% chance. So how many left-handed people are in here? I'm not, so I'm not going to. 1, 2, 3, 4. And how many people we got? 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 24, 26, 28, 30, 32, 34, 36, 38, 40, 42, 44, 46. Okay, and there were 4? And 46. So what's the probability that there's somebody's left-handed in this room? 4 out of 46, which is roughly what? Somebody help me out.
0.086 or 0.087.
All right, sounds about right. About 8% makes sense. And I think, the number that's still spouted is roughly 11% of the American population is left-handed. I don't know if that's current, to be honest. So that's pretty close. So again, 11% of the American public is left-handed means that any random collection of American people should have close to about 11%, right? If it's truly random. But again, that it should have. Most likely will. All those things mean it could be nobody. I wouldn't have been freaked out if nobody raised their hand. It wouldn't have freaked me out. If everybody raised their hand, would I have been freaked out? Yes, because the chances are so small. You guys should have just done it. Holy shit. All right. Sorry, I keep taking little side notes, but there's so much wrapped up in all this. Coming back to this, how many free throws would you expect Shaq to make if he took 20 of them, based off of what we just said, sort of? I would expect him to make 6. Where are they getting that 6 from? Yeah, if he makes 30% of his free throws and he takes 20 of them, I would expect him to make 6. Now, if he makes 10, is that freaky? I expect him to make 6. Is 10 freaky? Is 12 freaky? See, again, I keep wanting to preview this because we are going to talk about how do you decide where unusual starts, right? All right. And the other way, too. I mean, if you made 0 free throws, even though it's Shaquille O'Neal, I still might be a little freaked out about that. I mean, oh, that's not right. Right? Poor Shaq. Give him some. All right. How are we feeling so far? Okay. Yes?
Is it when it doubles its percentage? Is that when the unusual comes in?
No, I might as well tell you right now, since we know z-scores. Let me tell you what unusual is, because I don't think the book has said this yet. Unusual is normally considered to be outside of 2 standard deviations from the mean. And why does that make sense? Well, if it's the normal distribution, what percentage is within 2 steps, within 2 standard deviations? 95. So what percentage is outside of there? And if I told you something had a 5% chance of happening, wouldn't you say that would be unusual for it to happen?
Yeah.
Even if it's chubby dude, even if it's not normal, within 2 standard deviations, there's, who remembers? 75%, right? So there's 25% outside, so that's, that's a little bit further away. But we normally consider outside of 2 standard deviations, we call that where unusual starts, right? Later this semester, we're going to fine-tune that. It's not going to always be 2. Maybe sometimes it's 2.33. Maybe sometimes it's 1.645. It depends on the situation. All right, but that's later. How are we doing so far? So, since the question came up, I might as well tell you that. I keep talking about it. Okay. Oh, let's see. Blah, 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 blah. I guess I better come back down and just talk about it. So normally when you run an experiment, you do a certain number of trials. Thank God we're going to call that N. Like normal. The number of things I look at is N. I have a list of outcomes. The list of all possible outcomes would be called the sample space. That sort of makes sense too. It's a collection of all the things that could show up in your sample. We're going to do a concrete example here in a minute. I can define, put little bullets next to these, an event to be any subset of the sample space. So I have outcomes, or all the individual things that might happen. If you collect them all together, you put them into what's called a sample space. And then any subset of the sample space is an event. I can talk about the probability of an event happening. How are we doing so far? This is the exciting part of every chapter, is just talking about the words we're going to use. Blah, 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 blah. So let's do a specific example. That's a good idea. So let's say a couple has 4 kids. Well, let's not do that. Let's say 2 kids. 4 kids would be a really long list. Let's say a couple has 2 kids. What is the possible mixture of sexes of those kids? So it could be both. Yeah, so we'll say boy, 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 girl, girl, boy, girl, girl. I like it. How we do so far? Isn't that all the possibilities? It makes sense, because how many options for the first kid? 2. How many options for the next kid? 2. 2 times 2 is 4. So if I had 3 kids, how long would this list be?
6.
No, 2 times 2 times 2, 8. 2 options, and every one of those has 2 options, and every one of those has 2 options. 2 times 2 times 2 is 8. 4 kids, like I almost started with, would be 16. I don't know. All right. That would take just too long. So this, what I've just written, what is this that I've just written? What is that? What's the name of that thing that I've just written? Sample space. I love it. This is the sample space. They use the same terminology, right? Where'd you get this? All right, thank God. You good? All right. So outcomes would be boy, 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 girl, blah, blah. Each one of those is an outcome. Would you say any of those outcomes are more or less likely, or are they all equally likely? Roughly equally likely, to be honest. Boys are a little bit more chance to be born, because boys, we die earlier. So nature sort of somehow compensates for that. Do you guys know that? Men, we die earlier than women on average. So nature somehow figures that out, and the probability of a boy being born is a little bit more than 50%, and a girl being born is a little bit less. Well, let's pretend like it's 50-50. You with me? So these would be, I don't know, did I just bum people out? If you're a man, did you not know that we're on average we die sooner? I mean, you should know that, right? Doesn't mean you will die tomorrow. It just means on average men die sooner. So what was I just? Oh yeah. So these are all equally likely. This is very important. If they were not equally likely, I could not do what I'm about to do, or what I'm about to make you do. What's the probability that the couple has 2 boys? 1 out of 4. The only reason you could do that easily is because those 4 events are equally likely. The minute they're not equally likely, oh shit, we got to develop other ways to handle it. You guys understand what I'm saying? So we'll do an example in a minute where they're not equally likely. We're not going to quite develop all the math for it yet, but just to show you a situation where we can't do this. But this is 1 out of 4. Why? There's one thing that matches what we're looking for out of 4 total things that could have happened. So what's the probability that I have at least 1 girl? That's an event. That's an event. It's a collection of outcomes, right? Do you understand? So an event could be an outcome, or it could be any subset of this, any collection of those outcomes. So what is this probability?
3.
Yeah. 3 out of 4, right? 3 of these have at least 1 girl out of 4 total. And why does it make sense that these add to be 1? Or doesn't it make sense? They do add to be 1, don't they? Why does that make sense? Because together, don't they cover everybody? I like it. So these two events are what's called mutually exclusive events, right? You can't be this and that. This is no girls. This is at least one girl. Are you with me? They're also what's known as, more importantly for right now, these are complementary events. Which makes sense. They complement each other. They fill each other in. One plus the other one makes one.
So are complementary events always going to be mutually exclusive?
Definitely. I like it. In fact, it's by definition, I could call this event A, and then this one would be, I can't remember this book now, if it uses, screw the book. Yeah, I think it uses this little symbol for not A. This is A, this is not A. So if A is nothing but boys, what's not A? At least one girl, right? I like it. So if you have two opposite probabilities, they must add to be one, because that would be everything, wouldn't it? So I don't mean like, what about rain and snow and hail and sun and cloudy? No. Rain, not rain. There you go, done. Right? It covers everything. What about left-handed, right-handed? You have ambidextrous. Left-handed, not left-handed. Leave me alone. Right? You kind of with me? A little bit. All right. Okay. I'll make sure I don't miss any of these little freaking definition stuff. Blah, 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 blah. All right. That's beautiful. Let's do this. Let's do a very